Welcome to a lesson with Dr. Powell. Let's take a look at a way of expressing a sum of different terms in a sequence with a compact notation. All right. Suppose, for instance, um, I write down the following. Now, what in the world is this? It looks like Greek, and it is. It's the Greek letter sigma. Think S, sigma, sum. And all right, take a deep breath because it doesn't really mean much. Okay. Um, and it's maybe perhaps simpler than you're thinking. If I write down something like 2n plus 3, and I write something like n is equal to 4 up to 13, let's just see what this means. This symbol right here just means we're doing something with the sum. This right here actually gives us a formula for a sequence. So this sequence, a sub n, is equal to 2n plus 3. We can think like a1 is equal to 2 plus 3, which is 5. a2, in fact, imagine that, see this 2 right here, that's like the slope of a linear function or an arithmetic sequence 2. So we're adding by 2 every time. So 7, 9, 11, and so forth. In fact, so that's what this part means. So this part just tells us we're going to be adding up the outputs of this sequence, so the terms of the sequence, but we got to be careful. Where do we start? This tells us where to start. This tells us where to finish. In particular, the n value of where to start, so the index of where we're starting and the index where we're finishing off. So we're actually not even using these guys. We're starting at a4, and then which is 11. So we can kind of think, okay, so n is equal to 4, the output is 11, and we're going to be adding everything between. So this literally is just a sum. It's a sum of everything in the sequence in the list added together, starting at n is 4. So n is 5, the next place to 2 more, 13 plus 15 plus 17, and so forth until we get to n is equal to 13. That's the last thing that we're adding. Now we can just plug in 13 right here, and we see 2 times 13 is 26, plus 3, that'd be 29. Okay, so we're adding up 11 plus 13 plus 15 plus 17, skipping a number every time until we get to 29, and we're asking what the sum of this is. Now we can use our technique for finding the sum of an arithmetic sequence, where we take first and the last, we find the average of those two guys. And then we need to multiply that average by the number of terms that we're adding. So let's think about number of terms that we're adding. We start at n is equal to 4, and we end at n is equal to 13. Let's just imagine backtracking that a little bit. So we go 4 up to 13. Now, what happens if we subtract 3 from the 4, like shift all these indices down by 3? If we shift it down by 3, so subtract 3 off, we get to 1. Subtract 3 off, we get to 10. So that means the numbers 4 through 13 are just like the numbers 1 through 10. And there's 10 of those. Notice it's tempting to say, oh, I'll just subtract 4 from 13, but subtracting 4 from 4 here would take us to 0. Then we'd be going like from 0 to 9. But we want to go to 1, start at 1. So that's why we're subtracting 3 off to get to 1. Then we can subtract 3 off from the 13 to get to 10. So we know that we have 10 things that we're adding. So there's actually 10 numbers here. If we listed all these out, we'd see 10 of these guys. So we have 10 terms, and we take the average of the first and the last. We multiply these together. Now I'll do some cancellation here. 5 and 1. So 5 times 11 plus 29, and which is 40. And so we end up getting 200. So we have a sum of 200. Thanks for watching.